Again, let's welcome today's speaker, Professor Ebrahim Karimi. So again, for those who have logged in just for today, he has a BS in physics in 2001 from University of Kerman in Iran, and MS in physics in 2003 from the same university, from Institute of Advanced Studies. PhD he has from 2009, University of Naples in Italy. Currently, he is a Canada Research Chair Professor at University of Ottawa. Again, he works on so many things, but if he summarizes that his work focuses on structured quantum waves and their applications in quantum information. He has done a lot of fantastic works, and accordingly, he has a lot of papers, about 150 in all major journals, including Science, Nature, Nature Physics, Nature Photonics, PRL, you name it. He also has 3 patents in addition to all these publications. He's a member of several societies, including Royal Society of Canada, Global Young Academy. He's a fellow of Optica, formerly OSA, this time I remember. And he's also visiting fellow of Max Planck Institute of Science of Light, and of several other societies. Several prizes to his name: Ontario Ministry Early Researcher Award in 2018, University of Ottawa Early Researcher Award in 2019, Canadian Association of Physicists Herzberg Medal in 2020. He was the associate editor of New Journal of Physics until 2020, and he's currently the associate editor of Optics Express since 2016. So this was very nice, exciting 2 talks, and we are hoping that this will be as exciting. So over to you, Professor Karimi.
Thank you very much, and as we were just discussing, the speed is not so high, but as you mentioned kindly, we care about the context. So we care much about how much information is transferred. So as usual. So maybe that's a good sentence when we go to quantum communication. Anyway, so last time we stopped exactly at the beam shaping. So when the beam shaping, the technique to perform the technique that to perform amplitude and phase shaping plays a role, and we just discussed about the approaches that in order to have intensity to be imprinted to the beam, or specific amplitude to be imprinted to the beam, then you have to go with a specific algorithm. And the algorithm was given in the previous one. There are a lot of mathematics behind of that, but I think we just describe what we mean by those encryption. So far, we learned how polarization of light is associated to spin angular momentum, phase is associated to orbital momentum, and at the end also we talk about the way that someone can engineer amplitude and phase of an optical beam and generating a desired, let's say, mode in the laboratory. For the polarization, it was very clear that you can use wave plates, and essentially sequence of wave plates will allow you to do what we call SU transformation in polarization degrees of freedom. So OM and SAM, spin angular momentum, they were completely different quantities. Let's look at the spin angular momentum. And spin angular momentum is a bidimensional vector, as we discussed. So because that comes from the fact that that in vacuum, the divergence of F, which we introduced, Riemann-Silberstein vector, is equal to 0. So that forces that the electric and magnetic field in vacuum, they are orthogonal to the propagation direction. So, and essentially, in order to identify a vector in a plane, you need 2 independent vectors, and those independent vectors in the Cartesian coordinate can be H and V, and if you watch it, of course, it can be any orthogonal vectors that you may define. But essentially, the nature is bidimensional. Henry Poincaré, he had a very nice visual representation for that, which was a one-to-one mapping of what we call it SU2 group to S surface of a sphere, which is SO3. So essentially, if you look at the stereoscopic pattern and the way that this is mapped, essentially on the North Pole, you can have any North and South Pole, you can have any two, let's say, orthogonal vectors. Along the X, you can have any other two orthogonal vectors. And along the other axis of Y, you can have also any other orthogonal vectors. So traditionally, what we use left-handed and right-handed to be on the North and South Pole, and then H and V polarization to be on X-axis, anti-diagonal and diagonal polarization to be on Y-axis. So indeed, in this representation, usually H polarization or linearly polarized light beam is on the equator, and circular polarization is on North Pole. Excuse me. And indeed, anywhere else we have elliptical polarization. On the, let's say, North Hemisphere, we have elliptical polarization left-handed, and in the South Hemisphere, we have right-handed elliptical polarization. So just to tell and review again, North and South, they are circular polarization, equator is linear polarization, and any other places is elliptical polarization. So this is a very nice way that someone can watch it, and then any polarization optics, they will do an action, assuming that is unitary. Even if it's non-unitary, that's a different scenario. But any, let's say, polarization optics, they will do a rotation on specific polarization state on the Bloch sphere. For example, if I have a half-wave plate acting on, let's say, left-handed polarization, along, as soon as you go through the half-wave plate, you will see that the action of half-wave plate will be changing left-handed polarization to go to be right-handed polarization. This is a very simplified way. Essentially, that goes a little bit more complicated. It goes like such a curve. So it comes at an angle, goes to the equator, and then at another angle opposite way goes to the South Pole. So this is essentially the picture that you may consider. So, and the SU2 transformation that I mentioned is look like having two rotations from, let's say, along the pole to pole and parallel to equator along the equator. So you can move essentially this vector to any places that you want. Okay, and this is about the polarization of light. Now I'm asking you a question, and please answer to me. And the question is that, assuming that I have a half-wave plate, I go with left-handed polarization. And as we discussed, if we go with a left-handed polarization inside of the half-wave plate, at different thicknesses, what we will see different different polarization states. So essentially, the state of the polarization of light is changing from left-handed, and at the exit, what is happening, you will get right-handed polarization. So essentially, it moves like that. And the points are associated to different thicknesses. Okay, so at the end, what I have right-handed polarization. Now, the question is that, what is happening if I rotate the half-wave plate? What is happening with output polarization state of the beam? Any thoughts? Excuse me.
Output will remain the same, only the trajectories followed over the Poincaré or Bloch sphere will be changing, will change.
Yeah, exactly. So what is happening, as in a half-wave plate, if you rotate it, okay, to a specific angle, the output polarization state will not change. You can do a little bit of mathematics and you will see clearly that nothing changes on the polarization state of the output beam. Then the question will be, hey, I'm changing the geometry of the wave plate, but the initial state is not changed. The final state, it seems to us also is not changing. So if you do a little bit of mathematics, you will see, as Ruchi kindly mentioned, so essentially the trajectory that we do have is not going on the same path, but it goes on a different path. It goes here. And the initial and final states, it seems that they're identical. So we have a concept in quantum mechanics, which is formulated first by Pancharatman, and later on by, if I want to be precise, in a different concept by Yakir Aharonov, and later on by Michael Berry in much more advanced formalism, which shows that, okay, if if the system or the quantum state, which essentially this can apply also to single photon regime, is probing on a specific, let's say, trajectory on the vector space, if the initial and final states are the same, then you are expecting to get a phase, which we call a geometrical phase, that is associated to the projection or to the trajectory that is probing there. So the solid angle of the trajectory, and essentially for SU2 group, that is half of the solid angle. So what I want to say is that, okay, yes, the state is the same, but due to the change in the geometry, you will get a phase, phase changes here. And this phase change essentially is associated to the trajectory that is probed on the Bloch sphere. Fantastic. So, if you do a little bit of mathematics, you will see if the angle here is alpha, then the solid angle that you are probing is 4 alpha. So then if I change the half-wave plate angle by alpha, if I go with left-handed superposition, it becomes right-handed superposition. But then there will be an additional phase there, which is exponential of I omega divided by 2. And if I go with right-handed, then what is happening now, I am going from south pole to the north pole. So the trajectory, let's say direction is changed. And then the phase that I will get, it has a negative sign. So if the angle is alpha, then the solid angle will be 4 alpha. Then I'm expecting that both left-handed and right-handed, they will pick up a phase difference of exponential of plus minus 2i alpha, which the sign depends on the input polarization state. Beautiful. So let me use this technique to create a way that we can use it to shape a phase of beam, okay? Assuming that you have a half-wave plate, this is a half-wave plate that I can buy from any company, so I can get them and manufacturing by myself. Then this is the fast axis, which is labeled by these lines, okay? This is the fast axis of, or slow axis, it's up to you, fast axis of the half-wave plate. And then what I do, I cut this half-wave plate in slice of pizza. Okay, so I will make triangular shapes. And now I arrange them such a way that they have a specific topology like this. So the fast axis now is radially oriented here. So from a homogeneous half-wave plate, by cutting and placing them together, I will create inhomogeneous half-wave plate. So this is the half-wave plate that I created. And the angle between the two, I did a bit of mathematics for this drawing, is about 25.6 degrees. Good. Now, assuming that I will go with the left-handed polarization, and I will eliminate this alpha plate, which it is a little bit strange because it is structurally a half-wave plate, and I go with the left-handed, the output definitely will be right-handed polarization, as we discussed. So independent of the orientation of the half-wave plate, what you will get as an output, it will be right-handed polarization if you go with left-handed. However, point by point, since the orientation of the half-wave plate has changed, I will gain a different phase on the output beam. If the angle is 25.7 degrees, then the phase that the beam that is exiting from this part will pick up with respect to this axis is twice of that. So essentially, I'm going with the color coding. This is 0 phase, this is the pi phase, this is 2 pi phase. And what you will get if this line is the reference for us for, let's say, assuming the angle of 0, then these two parts, they will have 0 phase. These two parts, they will have the phase of 50.5 and 103, 154, 206, and etc. And finally, if you look at the color coding, you will see that it seems that the beam is changing the phase azimuthally, and it's changing from 0 to 2 pi and 2 pi to 4 pi. I can make the slice of pizza to be infinitely small, and then what I will get a pattern which is exactly look like this. So the phase is changing from 0 to 2 pi and 2 pi to 4 pi. So this approach, I mean, just to mention, by the way, this is look like the phase that you will get is look like having double staircase, and this I think is a church in Italy, which very likely what they want to see, they want why they have two, let's say, staircases, because maybe the priest that want to go up doesn't want to see the priest that is coming down. Anyway, so essentially with these approaches, we were able to link spin angular momentum, which is polarization, to the phase of the beam, which is orbital momentum. So this device works as a spin orbit coupler. And due to, let's say, the center singularity, because at the center, what is the orientation of the half-wave plate? If you remember the orientation, they were radial. If you go to the center, there were no definition for orientation of the half-wave plate. Then most of the light at the center will be scattered off and will go to the periphery. So the intensity profile, it becomes a donut shape, which is the property of the beam that carrying orbital momentum. This device was invented by my PhD supervisor, Lorenzo Mariucci in Italy, and he named it Q-plate for the reason that you have a specific topological charges there. I helped with the development of the theory of what is going on with the beam propagation, and also with the experiment, how to control the retardation of these and how to control the beam, and more extensively on what are the output beams and getting the structured light beam out of these, like lemon, star, and many other things there. Anyway, if I want to simplify the action of a Q-plate, by the way, this Q-plate is cylindrically symmetric. Essentially, you can create any type of Q-plates with any topological charges. And I will describe what I mean by topological charge for the Q-plate. So for these azimuthally oriented, let's say, device, which essentially in the laboratory, we don't cut really half-wave plates to do that. We use a technology which is liquid crystal one. And in the liquid crystal technology, essentially the liquid crystal molecules, they will orient, and since they are birefringent, it seems that you don't have any problems with the resolution there. although the fabrication in such a way that those liquid crystals, they will be oriented, is limited by the resolution of the fabrication that you have. However, at the end, if I want to simplify this, is that if you go with left-handed, you flip the polarization, it becomes right-handed, and then you will get orbital momentum of 2. If you go with right-handed, the polarization will flip, and it becomes left-handed, and then the beam carries orbital momentum of -2. So it's a spin-orbit coupler. I don't know if I have the equation here. Let's go here. I don't have the equation. So if you remember, left-handed polarization had plus h bar angular momentum. This is spin angular momentum. The initial beam is Gaussian. It doesn't have orbital momentum value, so the OM value is 0. This system is cylindrically symmetric, so I'm expecting that there is no impart of orbital momentum to the beam, because based on the Noether theorem, this is rotationally invariant. The polarization of the beam is flipped from left-handed to right-handed, then spin angular momentum of the output beam is -h bar. And then I'm expecting to get orbital momentum of 2, which means that I have 2 h bar orbital momentum here. So the sum of the spin and orbital momentum J is h bar here, the same for this in. For output beam, this is equal to -h bar plus 2h bar, which is again h bar. So this perfectly makes sense. So what is happening essentially, since you are flipping the spin angular momentum, the system is cylindrical symmetric, then it should pick up another sort of angular momentum, which is orbital angular momentum. This device is called spin to orbital angular momentum converter. Okay. And this plays role in when you deal with quantum walk, which you want to have a device that can couple spin and orbital momentum together. There was something else that I want to tell. And if you recall, for the SLM, we were limited to less than a kilohertz to manipulate the beam. But here, in order to change the orbital momentum, you need to change the polarization of the light as input light. How fast can you switch the polarization? Essentially, you can easily go to mega and gigahertz. So these are a fast way also to manipulate the orbital momentum. So by just flipping the input polarization, you can switch the orbital momentum at the output port beam. Beautiful. Okay. And this is the approach that I mentioned that is related to how to manufacture these devices, and in any arbitrary topological structure, which is the liquid crystal technology. Essentially, what you have a piece of glass, ITO glasses, which is a conductive one, and then you have you coat a polyimide on the other side. So we coated a polyimide there. We have an identical glass on the other side, which I don't want to show, that the polyimide also is coated here. Then we use a UV light to change the orientation of the polyimide here. So this is that pixel by pixel, we align the orientation of the polyimide. And then when you insert the liquid, after the aligning the polyimide there, if you insert the liquid crystal between the two plates, what is happening, the liquid crystal will look for minimum interaction between the two plates and picks up the orientation that the polyimide they have. So with this technique, you can imprint a specific topology to liquid crystal by arranging the polyimide on the surface. So I'm sorry, let me just erase the, okay. And the setup is look like that. essentially. So we have a 405 nanometer wavelength laser. It goes to a DMD, which DMD is pixelated, and we will synchronize this DMD with a half-wave plate here. So these two are controlled by a computer, and then we will say that each part of the sample will receive which kind of polarization, which the polyimide will react to the polarization of the light, and they will form exactly in the direction that the polarization is there. And the spacer that you have in between the part of the sample is almost about 4 micrometer. So with this approach, we were able to generate almost arbitrary polarization states, including, for example, there are few cases here. You can create in Scotia beam, and you will see that this is a very low resolution pattern written with the polyimide, just to show to the people that really we do have the control. So each part of these, they have a specific orientation, and then these are the orientation of the polyimide in those regions. And then if you shine a Gaussian beam on top of this sample, you will create, let's say, in Scotia beam. And if you go do the interferogram, you will see that there are phase dislocations at different places here. For example, one is there, one is here, the other one is here and here. And you can create also airy beams, very complicated airy beams as well, or a beam that carries high value of orbital momentum. And this is the sample that was fabricated by Hugo Larocque, one of my ex-students. And if you zoom in, you will see that you will get, and by the way, this is a superposition of e power of I 200 phi and plus e power of minus I 200 phi. So essentially, it's a superposition of two different orbital momentum values, because we want to just count how many OM values do we have, how many phase jump do we have along azimuthal direction. So these are the approaches. Do you have approaches to generate OM values? So people, they translated these in, for example, plasmonic structure. They created a spiral faceplate using the nano antennas, or I created, for example, liquid Q plate with the plasmonic range, and by just orienting nano antenna in a specific topologies. And anything that you see is mainly based on that. I did not mention, however, the original way that people, they created orbital momentum, which was inside of a cavity of a laser. So inside of a cavity, they forced the cavity to be excited in the Hermit Gaussian mode, and then they had a pair of cylindrical lenses to convert Hermit Gaussian modes to Lagrange Gaussian modes. So now I think before going to the detection system, we can have, let's say, questions if there is any.
Yeah, I have one quick question, maybe two. So the last one that you showed with the OAM of a 200, was that using the deformable mirror or? No,
it was liquid crystal.
Oh, liquid crystal. Okay, okay.
It was what we call it Q plate. So we used deformable mirror to manufacture the Q plate, but the results, they were made by Q plates and not with deformable mirror. So we have never used deformable mirrors to create orbital momentum.
Okay.
In our laboratory.
Okay, so these Q plates are now being made by these liquid crystals, so that you can have kind of almost infinite resolution as far as how many sectors you can add to make the whole circle. Is that?
Exactly. So this is the concept that we just discussed. So we are creating pixelated half-wave plate, okay? Mm-hmm. And each part of the half-wave plate is oriented, I mean, the fast axis is oriented in a specific topology, right? So you can do whatever you want here. And this is the setup that I showed to you to create the segmented half-wave plate.
Okay.
Okay, as soon as you enter with any polarization left, then since the halfway plate, the orientation of the halfway plate is a function of x and y, then output beam becomes right-handed with a phase which is given by I to alpha, which is the function of x and y. So this alpha indeed can be any value. So for example, for a Q plate is Q phi plus alpha 0. Then it means that the beam will pick up exponential of I to Q phi plus, plus 2I alpha 0. And if you look at this term only, this term is e power of I to Q phi. And this is a sign of carrying orbital momentum, right? Mm-hmm. What is the value of orbital momentum? Is 2Q. Then, if in order to create orbital momentum, Q must be half integer. Either it should be 1/2, 1, 3/2, of course, absolute value I'm mentioning, or 2, and etc. Mm-hmm. Okay? So now I can go back and I say, hey, I want to create Q equal to 1, which means that I'm creating orbital momentum of 2, right? And what does it mean that what does it mean? Oh, let's go with something a little bit more complicated. Don't go with easy question. So I think you can follow this discussion. Now the problem is I want to create Q equal 1/2 because the beam that is exiting will have orbital momentum of 1. So the question is like that. So I'm going with left-handed, I will get right-handed, but I want this factor to be exponential of I phi, right? Mm-hmm. And I want to understand what is alpha here, mm-hmm. which alpha was given by Q phi plus alpha 0. Mm-hmm. So let's look at the topology. And alpha is the orientation of these halfway plates. So this is the angle of alpha, essentially, how they are oriented here. So at alpha equal to at phi equal to 0, then alpha is equal to 1/2 of phi plus alpha 0. Assuming that alpha 0 is 0, it can be any arbitrary value, but it doesn't matter. Then alpha is 1/2 of phi. At phi equal to 0, then alpha is equal to 0. So for all of the beam here, all of the liquid crystal here, the orientation should be like that because this is 0. At alpha equal to pi divided by 2, sorry, that phi equal to pi divided by 2, then the orientation should be equal to alpha should be equal to pi divided by 4. So it means that the orientation of the liquid crystal here, they will be like this. Yes, they will be like this, which is with respect to x-axis, they have the angle of pi divided by 4. Now I'm asking that at phi equal to pi, what is the orientation of liquid crystal? The orientation, they are equal to pi divided by 2, because remember this equation. Then here, in terms of the orientation for them, oh, sorry.
Vertical line.
Exactly, it will be like that. And the same scenario for this one, it should be added 1. And going back to the same place. So if you plot them continuously, you will get such a topology for the halfway plates, okay? And this is what I mean by topologically structured halfway plate. And this is what in general we call it them Q plates. Mm-hmm. And for this specific case, Q is equal to 1/2. Now I know that if I impinge a circular polarization like beam with L equal to, with a left-handed polarization, then after this halfway plate, this structure halfway plate, I will get right-handed with orbital momentum of 1. Is clear?
Okay, yeah, fantastic. So what is the generation efficiency of these versus the SLMs? I mean, as far as...
Oh, yeah, exactly. This goes back to the question, how quick can you switch between left-handed to right-handed? Gigahertz. We can do that with the focal cell. So the input beam can be flipped from left-handed to right-handed very quickly, right? Then the output beam will flip from right-handed with orbital momentum of 1 to left-handed with orbital momentum of -1 very quickly.
No,
so
I meant the power conversion efficiency. Suppose I come in with the mode.
Is 100%.
Oh, wow. Okay.
Yes, is 100%. That's the reason that any experiment that we do, but usually we use QuIC. We don't use other devices. And moreover, it is a single beam. So it means that it really look like a piece of halfway plate, like that. As soon as you get in, from the output, you have the beam that you wanted. It's not diffraction. And it's not look like having gratings and you have to change the beam direction, having half meter after that with the 4F system to filter out the beam.
I see. Excellent. And since these are liquid crystal devices, I'm assuming these will be, you can address them electronically, right? I mean, these are not...
Absolutely. Absolutely. If you want to do that, that's a different scenario. Yes, we have done that as well. So we apply the electric field. That's the reason that we say that, I say that we made it with ITO glasses in Ottawa, because you can apply the voltage on the top of the switching the polarization. Then you can have a different way to control the Hilbert space, essentially, to include the zero as well, and also creating very, very rich topologies.
So are these commercially available?
No, I can, if you want, I can send you a.
I see. So these are fantastic.
I will be more than happy. I mean, I will do that. I don't know, maybe at least 20 or 30 groups, they will get it either from me, or I'm sure that also they will get it from Lorenzo.
Excellent. So regarding for example, if I'm using an SLM, I mean, of course, the efficiency, we know what it is. I mean, you can't get more than 10, 15, 20%. But there I have the flexibility of choosing any shape I want. But is that also, I have it here, let's say L equal to 1 to, I definitely can go up to L equal to 40, 50, given the size of my kind of SLM. So is that kind of range also possible with this?
So in order to arbitrarily switch them between different ones, you have to cascade them. You have to cascade these Q plates. So you have one Q plate, another one, another one, another one. So depending on how many you have, you can switch from -L to +L, which -L to +L can be almost 20 modes or even 25 modes.
I see. By electronically switching on
and off. Okay. Exactly. Make them to look like a full wave plate or half wave plate.
Okay.
Or even you can go with a quarter wave plate, then you will get even more rich topology.
Fantastic. Excellent.
Sure. And even I think in 2012, or 11, I don't remember. I have done another seminar work which I kept the Q plate inside of a cavity, and as soon as the beam is going inside, and at output port, I had a little bit of leakage, which I could pick up beams with different OM values. So it was what I call time correlated, being correlated to OM value. So different timing, you had different OM values.
I see. Excellent.
Sure.
Okay, so yeah, so I'll keep quiet now. So other questions, if anybody has.
Let me get a glass of water, sorry.
Okay.
No questions?
Yeah,
I hope that it's not difficult.
Yeah, no, I think we're fine for now, so you can go ahead.
Sure. So the detection part is very important because the devil is in detail as usual, and this detection part is very complicated essentially, and many people they miss the details there. So far we have wavelength that can be controlled. We have polarization that can be controlled. We have radial part that also can be controlled. We have orbital emitter. Essentially, this part is what we call it spatial mode. I did not talk about temporal, by the way. Temporal is a different scenario. So you can create a beam or a photon, a single photon, which is a coherent or incoherent of all of these degrees of freedom. Now the question is that how can we detect them? How can we understand what are those coefficients? Okay, when you have all of those degrees of freedom playing a role, then the complexity appears in detection system. And this is very, very difficult. It becomes extremely difficult. So having polarization and spatial mode, having wavelength polarization and spatial mode will bring us to a different level of complexity. Let me give you an example. Assuming, I think one of the students last lecture or the previous lecture, they asked what is going on with incoherent superposition of different OM carrying beam. I think he mentioned having L equal to -3, -2, -1, and 0. And I say that if it's incoherent, then at the end, you will have just, well, you know, some of the intensities, and then it will be a very, let's say, in-uniform intensity profile. Now, I don't talk about incoherent one. I don't talk about the density matrix here. Instead, I would prefer to work with a coherent superposition. So I do have a coherent superposition of L equal to 0, L equal to 1, L equal to 2, L equal to 3, and also the others. Okay, so essentially, this is equal to CL L, which L is changing from -infinity to +infinity. Essentially is unbounded, and the bond, it depends on, you can choose from -m or M1 to M2, depending on the experiment that you are performing. And now the question is that what are C0, C1, C2, and C3? Okay, guys, how do we do that? Any idea?
Tomographic measurement or something.
What?
State tomography otherwise means C0 is a complex number.
You do the state tomography. Okay. How do we do that, Suman?
I don't know that exact procedure. Maybe by mutually unbiased basis or something.
Beautiful, wonderful, so amazing. You are totally right. We have to do the quantum state tomography. Let's go and go step by step and see what we can do with this. But Suman is perfectly right. I mean, it's exactly the procedure that you have to do that. And this is an example, by the way. I don't remember it was Suman or someone else that asked this question. This is the M1 and M2, which is, I put it here, so M1 is equal to -3, M2 is this one. And the coefficient that I put it here, it is equal weight for all of them. And the relative phase between them, because these C0 to Cn, they are complex quantities. They can be, they can have a phase, they can have a different relative phases, or they can have a different amplitude. So this is a very, very simple case, which you have L equal to -3 to +3, and all of them, you sum them up together with equal weight and relative phase of 0. The beam that you will get it at the end is like this. It looks like a slice of pizza with a little bit of tail here, okay? And if you look at the phase pattern, this is a 0 phase and this is a pi phase. So you have the line of singularities here, phase singularity here. Clear? This is an example. And the problem, don't forget, how do you define CLs? Fantastic. And this is the beam. And what we want to know, make it simple for the time being. Don't go for the big challenge, go for the easy one. How can we find the intensities of them? So essentially, how can we define the C0 power of 2, C1 power of 2, and etc. Okay. The procedure that we will have is that if you go to the far field, you know that the components of those, they have a donut shape, and this one, no, doesn't have a donut shape. So essentially, I have to look at the inner product of the modes that I have with the state that I do have it here. And in order to find the intensity of probability, what I have to do, I have to look at for the square modulus of these. So this is the concept. So essentially, I have to make L psi square modulus in order to get CL squared. Good, let's do that. So what are the spatial distribution of each of them? So is Gaussian, is donut, is donut, is donut. So if I put a iris is a pinhole in the far field, then I can pick up the intensity associated to each of them. So for example, I can place it here, then I get the intensity associated to L equal to 0, while if I move it to the next one, I won't get any. If I go to other one, I will get even less. Okay? So the approach that we use, they call it projective measurement. And in order to perform projective measurement, you have to have, let's say, a couple of iris or 2 iris in near field and far field, such a way that they will allow you to pick up specific mode for you. And this is the entire procedure. For example, for L equal to 0, it's easy because a simple iris does the job for us. However, when you go to L equal to 2, L equal to 3, and others, we have to use the other approach, which was the holographic approach. And in the other approach, if you remember, the hologram worked as OM adder. So if you go with L equal to 0, you could add L equal to 2, depending on the pattern that you had it on the hologram, to initial beam and getting L equal to plus 2. However, if you change the OM value to -2, then since this is adding an orbital momentum of 2 to the beam, then you will get L equal to 0. So by putting a different hologram, you can shift the OM value of the beam up and down. And let's do that to do the experiment. And essentially what people, they do, after this hologram, they have a fiber, single mode optical fiber, which essentially works as look like a pinhole exactly, and picks up only the Gaussian component of it. Let's check. So now instead of a pinhole, I'm putting a fiber, and the mode of fiber is Gaussian approximately. So if I have the beam and directly coupling to a fiber, the component that I will receive is the Gaussian part. So essentially, I will get the C0 square modulus. However, in order to get the C1, what I have to do, I have to transfer the mode of C1 into the Gaussian one. What I do that, I will just place a hologram. I will insert a hologram to the beam. So essentially your beam, the psi was there, right? Then I will put a hologram here with L equal to -1. And if I have, oops, sorry. It's a little bit difficult sometimes to write that. So I have the beam, I have the hologram with L equal to -1 to be imparted to the beam. And previously I had C0 L equal to 0. I had C1 L equal to 1. I had C2 L equal to 2, and etc. Now, after the hologram, what I will get, I'm shifting the OM value by -1, so that becomes C1 L equal to -1, C1 L equal to 0, I have C2 L equal to 1, and etc. So then, by switching the hologram and just making to be L equal to -1, then I can shift the state here, not the coefficient, to be a Gaussian one. And then now this mode will couple to the fiber. And I will get C1 square modulus as the power. Then the same scenario, I can now insert L equal to -2 hologram. Now, all of the modes, if you do the calculation, you will see that the mode of 2 now becomes 0. Then this one now will couple to the fiber, not the rest. And the same scenario for L equal to 3. And I will get all of the coefficients. So essentially, in order to perform, not really here quantum state tomography, but the projective measurements, what you need a dynamic hologram, which is changing the L value to to -m. Then after that, you have a fiber, which is captured on the first order of diffraction. Then from the fiber and the power meter, I can read the Cm power of 2 coefficient. And that was the input beam, which is psi superposition of all CL L values. Clear? However, this was first, I think, proposed by Anton Zeilinger and in his famous Nature paper. And they properly handled the entanglement generated in spontaneous parametric non-conversion, and widely used by many other scientists in the community. However, one thing that you should remember is that sometimes physics gets more complicated and you should handle it properly. Remember that the mode of the fiber is not Gaussian mode, a truncated bezel. And if you be in different field, if you have different, let's say, beam waist, even the simple case, which is Gaussian profile, being coupled to the mode of fiber, if your fiber is a different regime, or let's say different range, even the matching of the fiber with the Gaussian profile is not the same. You have seen that in the laboratory. When you do coupling to an optical fiber, essentially what you have a couple of lenses, objective lenses, and also a couple of 4F system or telescope system to reduce the beam waist of the beam such a way that is matching the fiber size, and essentially doing the transformation in such a way that the beam waist is in the range of the dimension of the core of the fiber. And you will see that even if I send two people to the laboratory, depending on the equipment that they have, they can get different coupling efficiencies. The same scenario happens here. Essentially, the hologram, what it does, it takes away the phase information of the beam. Remember, I have L equal to 1. I'm going to a hologram. I will erase the phase information. This is what hologram does. It takes away the L orbital momentum. but will not modify the intensity profile. So at the output of the hologram, I have a ring-shaped intensity which doesn't have orbital momentum. When you go, if you go to the far field, I will see the diffraction from these, and then essentially I will get a central peak with a ring around that, which is the nature of being a truncated beam. If I go with L equal to 2, and then putting a hologram with L equal to -2, then I will erase the phase information. The beam is not anymore shape invariant, but immediately after the hologram, I have a bigger ring with no orbital momentum. If I go to the far field, I will get again the same intensity at the center, and a periphery which has a little bit higher intensity compared to L equal to 1. So then what is happening? Different mode, after being flattened, the phase being flattened, going to the far field, they have a different intensity profile. And then they will not couple equally to the mode of the fiber. So the phase flattening technique has a bias in some cases. So that should be handled very carefully. And these, I think, are the experimental results that we obtain in the laboratory, and saying that, hey guys, if you go with L equal to 1, and this is the ratio of the beam size compared to the dimension of the fiber for different values. So for example, if this is equal to 0.2, then you make a line here, you will say that L equal to 0 has, let's say, about 10% efficiency. L equal to 1, 2, 3, and 4, they have almost 20% efficiency of being coupled. If you go with, let's say, the beam size, which is almost the ratio that is equal to 0.6, then you will see that all of those modes, they have different ratios, so a different coupling ratio. And this will play a significant role when you do the quantum state tomography, because it seems that your projective measurements depends on the mode that you are projecting onto. So either you have to characterize the system prior to do the quantum state tomography, or you know exactly what is going on in the system, then you do a little bit of mathematics and you will handle them properly. So if you want, I mean, those are the experimental results, which is confirming exactly the theory for different cases. And by the way, these regions are not trustable, essentially. Okay, so these are the detection technique. I think now I'm done. There's another one. Let me see, what time is it right now? It's 8:30. I have half an hour, and this half an hour I can go with quantum key distribution, guys. Or if you want, I can just follow up the basics.
No, I think you can go ahead with some QuIC results. Yes.
Sure.
I had a couple of questions. Is the right time?
Yeah, absolutely. Absolutely. You can ask question anytime that you wish.
Yeah, so first one is a simple-minded question that when you're finding this coefficient C0, C1, C2, can one actually just interfere, since you know the beams, can one interfere with another artificially created 0 and 1 and 2 and get the coefficients that way instead of using the aperture technique?
I did not get the question, Saket.
I'm saying that this state psi, which you wrote as C0 times the 0th mode and so on. So if I want to find C1, for example, I can interfere with mode 1 of the entire field, and that will pick up, because the states are orthogonal, that should in principle give me C1. Is that the right way of thinking? Or?
Just looking at the interferometer?
Yeah, interferometer, but by changing each of these, like the same beam, I interfere first with 0, then with 1 and 2 and so on, and then get the intensities. Is that a possibility?
I don't think so. I don't think so. That I don't believe that the interference will allow you to see that. Let me think. If I look
I'm
at
saying
it
take a pure zero state and later take a pure 1 state and 2 state. In some ways, that's kind of what you're doing, right? Shifting and like projecting it on 0.
Yeah, no, be careful, because if I don't have the fiber, I cannot pick up. The point is that this is the hologram that I have, okay, and this is the beam that is coming in, which is the psi, is a complicated one. Then at the first order of diffraction, I have the fiber, right? And I will read either the photon count, I will read the power of intensity from the fiber, okay? So what is happening? Psi essentially is the superposition of CL and L. Hologram, what it does, it changes CL, it changes L plus M, okay? This is after the hologram.
Yeah.
And then the fiber, what it does, fiber will pick up only 0 state. That's the entire action. Because the mode of fiber is a single mode optical fiber, is 0 carrying orbital momentum.
Right.
Okay, so essentially at the end, what you have 0 doing the linear product with psi after the hologram, which is shifted essentially. So it's 0 dot, let's say, all of the C's, so C1 1 plus M plus C2 2 plus M plus C3 3 plus M, and etc. Okay, and then at the end, I'm not able to read out these detectors. What it sees the square modulus of that. Okay, so now the hologram, if you change the hologram M value, then the inner product which is happening here will show up. So for example, then you have C1 0 1 plus M and plus other terms. Okay, only changing the M value to, for example, M equal to -1 will give you C1 square modulus. Changing to 2 will give you the C minus 2. Changing to -2, it will give you the C2 square modulus, and etc. So without the single mode optical fiber, essentially you cannot do this projective measurement at all. Clear?
Yeah, that's clear. Yeah. So the other question I had is, how good is this the wave function? How far one can take the wave function approach? Like for example, like like if I have these beams, I'm not an expert in this field, so it might also be simple-minded that like I have this LP polarizations, all this complex mode superposition, and then I am focusing down with a lens on a fiber. So isn't it very quickly, due to propagation and diffraction and so on, getting into a mixed state? Or
no. So the coherency will not be affected at all.
So
remember,
the pure state approximation is still good?
Pardon?
The pure state approximation is still fine, like the pure state wave?
Yeah. So there are two important points. So your question is that, okay, fine, I start from a coherent beam.
Mm-hmm.
Is it possible to get a decoherent beam? Yes, it is possible. If you get the beam to get entangled with environment, okay? Since you don't have a knowledge about the environment, you are tracing over the environment state.
I'm not talking of the environment. I'm not talking of the decoherence and environment. I'm just saying that I start with a pure state, but this degrees of freedom just due to propagation. No, this happens in quantum mechanics often, that even without an environment, just evolution can make a pure state very quickly mixed state.
So, just
When you have many degrees of freedom, they start getting mixed. And particularly here, when you are actually focusing down, you know, your P, L, pi, all these are getting mixed. So that from that point, I understand that these are like completely free zero temperature systems. There is no recurrent system, but nevertheless, just propagation itself can make it mixed state, right? And
yeah,
that's
so
what
I got your question completely. Okay, so
yeah.
We have done so many experiments on this direction as well.
Yeah.
So how the decoherence will happen among the particle
among the larger Hilbert space, yeah.
Particle states.
Exactly.
Exactly. So this is what happens. So assuming that you have complicated polarization states, okay, you send it to, even we did not talk about that, you can send it to a tightly focused regime. In the tightly focused regime, everything gets very, very complicated. It becomes, let's say, longitudinal component of the field will excite it, you will get Möbius strips and etc., depending on the state. So as far as you know the states, you can perform the measurement on P, L, and polarization, then you're okay, because you know the entire state. As soon as you have the lack of knowledge about one of those degrees of freedom, then you will get partially mixed state or you will get a mixed state. Okay? But we know techniques how to do the general state tomography, so which is means all of those degrees of freedom doing the tomography on them.
I see, okay.
Okay.
So since here you are preparing the state, well-known state, so then you have a complete knowledge basically.
Exactly. We can do the preparation, we can do the manipulation, and we can do the detection very clearly.
Okay. Great.
There are challenges there, but I think depends on how good you want to go. So, for example, one of Saikat mentioned the mutually unbiased basis. What is the mutually unbiased basis for dimension 6? I'm sorry, I don't know. It's an open question. But I can go with or complete state tomography, even in dimension 6, or I can go with SIG POM, which is symmetrically information complete basis. So there are ways that we can solve the problem if you are not asking for optimal, okay?
Okay, okay, thanks a lot, thank you. Yeah.
Absolutely. Look, I could go directly with these, let's say, very deep concepts, but essentially, without knowing the basics, is almost impossible. Good. So let me see what I have. I should have something here. Okay. I'm sure that you are familiar with SPDC. I don't need to go through these. And detection, sorry, it was very long lecture for people. Okay. So these are the example of high dimensional states. So for example, I can go, I can create these 6 states, which is essentially from -3 to +3. So I have the 6-dimensional Hilbert spaces is an example of psi. And then also I can go with the superposition of all of those states, CL, L from L equal to -3 to 3, excluding 0. Then this is one option, as I say, this is one set of mutually unbiased bases. I can go with a different CL, I call it CL prime, then I will get L equal to +3 to 3 as well, sorry, -3 to 3, excluding 0. And these are another set of that. And now the question that I have for you is, guys, they are both, I mean, let's say if you look at this one and this one, they both have, they are both coherent superposition of L equal to -3 to 3, but with different phases. And you will see that the intensity profile is like that, the intensity profile of that one is like that. They are very different. What are the coefficients? This is what I mean by doing the state tomography, or by one of your colleagues that mentioned. You can go even with very more complicated one. This is what I call a SIG POVM. And essentially, the number of states that you have, it is 36 states. And if you do the projection on these 36 states, essentially you can get the entire the wave function, not only the amplitude, let's say the square modulus of the coefficient, but also the entire the CL coefficients completely. Okay. Anyway, those are the examples, and also those are the polarization and OM mixed together. Not mixed. I mean, using both of them for encryption. So the importance of orbital momentum. Now, I will go briefly in less than 20 minutes with OM and why this is important for quantum communication. Assuming that we are sending a letter M to somewhere on my computer, depending on the CPU that I have, this letter M will be translated in binary code. So here is, if it's 32 bits, it will be encrypted, or let's say it will be in ASCII code of, let's say, 1 zeros of 8 of them. And essentially, if I do the communication in 32 bits, these will be sent in 8 signals, and each signal they will have specific information in. And for example, they use the wavelength to clarify this. So for example, the wavelength of orange here, let's call it orange, 800 nanometer is associated to signal 1. And if I go with 400 nanometer, it will be associated to a 0 mode. And then I can send the information, and from the other side also they do the detection, and then they will understand if I'm sending this sequence or other sequence of code. However, going to higher dimension gives you the possibility not sending in binary, but sending in higher dimension. For example, I can go from minus 128 to plus 128, excluding the 0. Then I can send 256 mode, essentially, without sending, let's say, more than one bit, one photon. So each of those modes, they will be associated to one of those, let's say, 8 signals. And then instead of sending 8 signals, I can send 1 signal. This is the importance of having access to higher dimension, and is entirely classical. However, we can do the quantum cryptography, and just to review briefly that why the quantum cryptography is important, because in the quantum world, the first thing that we know that there is no definite reality. So the big example of that, an important example of that, is Schrödinger equation, which Schrödinger want to say to people that how quantum mechanics is important, because there we have superposition, while in the classical world it is a little bit awkward to have superposition. How is possible that the cat will be alive and dead at the same time? What else we do have in quantum mechanics is uncertainty principle, which tells us that the conjugate quantities, they cannot be measured simultaneously. So everything in the quantum world has a limit, and explicitly the conjugate quantities can, they are restricted within certain, let's say, limits. As a consequence of the these, also what we have a cloning problem. So we have no cloning theorem. Since we cannot measure X and P at the same time, then it means that also we cannot define a quantum state. Or let's say if someone gives us a quantum state, we cannot perform a measurement and understanding what is the quantum state on a single ensemble. So either we have to measure X or we have to measure P. So we cannot measure both of them simultaneously. So, and as a consequence that we have no cloning theorem. No quantum state can be cloned perfectly. And just to tell you, without going into deep mathematics, although the cloning is just 2 lines of equation to prove, assuming that someone gives you a quantum state, without knowing the quantum state, you can make a copy of that. Then you can measure X on 1 copy, you can measure P on 1 copy. Then you are violating the uncertainty principle. So the cloning then is against the Heisenberg limit. So this is the problem of the no cloning. In the quantum cryptography, essentially we are using this concept, which if I want to go deeply, it will be the contextuality concept. So Alice and Bob, they want to do the communication, and usually in the current world, what they do, they have a public channel that they send the signal to each other, and anyone can have access to this public channel and getting the information there. However, this is a kind of message that can be shared in the public channel, and you can see that it doesn't make sense at all. However, Alice and Bob, they share a key in a secure channel, which this key will tell us how to decrypt the message. Okay. By the way, this is the old-fashioned one. The current one is very different. It is based on an RSA protocol. And RSA protocol is look like sending luggages all around the world openly and asking the other person to put information inside of the packages and send them back to you. And you have the key to open all of them, okay? So it's a different protocol, it's a different strategy, but this is very easy to understand. So public channel, the message, encrypted message is sent there, and in a secure channel, what you share is a key to read them. So for example, these the what they call shifting key, the cipher key that I have, it is swap one, and just replacing one of the alphabet with the other one, and you will get the message, which is a nice poem by Khayyam. In the quantum world, what we do, we use this property of quantum mechanics, which on conjugate quantities, they cannot be measured simultaneously. So we use position to send the information or momentum to send the information. But we know that if you don't know which one is used, then you cannot perform the measurement and revealing the information properly, because you have to know if you have to perform the measurement on X or you have to perform the measurement on P, because you cannot measure them simultaneously. So X and P, they are continuous quantities. So we have a similar definitions for discrete quantities. So here in this case, I'm using binary code, or let's say bidimensional vector. Essentially, the Hilbert space that I have is either this one, which is an orbital momentum of 1, or let's say -1 and 1. And this is look like X for me, the X space, or is P, which is the Fourier transform of this, which is -1 + 1 divided by square root of 2, -1 - 1 divided by square root of 2. So this is look like P for me, this is look like X. So without knowing the basis, I have no idea, and I cannot measure X and P simultaneously. Okay? Just to understand, this is the important part of the game. So you are encoding in conjugate quantities, which is look like, I call them circle and plus. So, and in the secure channel, Alice and Bob, they share a key even without knowing it prior to sharing. So Alice randomly picks up one of these bases, either circle or plus, and sending the information that she wanted. So she's sending, for example, 0, 1, 1, 1, 1, 0, 0, etc. to Bob without even telling Bob what is going on here. Okay? Bob knows that the information will be sent in these two bases, circle and plus, but Bob doesn't know what Alice is sending. in which basis she's sending the information. So Bob randomly picks up, let me just erase these, all of them, just to get a clear picture. Okay, Bob doesn't know which basis Alice is sending the information. Then he randomly picks up one of those bases and performing the measurement there. So this is what Bob does. For example, in the first case scenario, Bob performs the measurement in the wrong base. Then after doing that, Alice and Bob, they talk to each other on the phone. Alice sends to Bob that for each signal or each photons that send, which basis was chosen, okay? So she does not reveal the information. What she reveals is that either it was plus or it was minus. So for example, now Alice says to Bob that for the first one, I choose circle base. Bob says, I'm sorry, they discard that. For the second pulse, they send in the plus basis. Bob says, yes, I was in the right base. The fourth pulse, right base. And let's say the eighth pulse, let's say signal right base, 9 signal right bases. Then after that, they know that which signals they have to trust, even without revealing the information. Since Bob knows that he was in the right base, he trusts to the results of that he got it from being in the proper projection basis. Good. With this way, even Alice and Bob, they did not talk to each other, but now they have a key, and the key is established afterward. It's more complicated than this. Sometimes they have to compare the results just to understand if whether they are they got the same results or there are someone interrupting the channel. For example, let me tell you until here, I think everything is clear for you guys. So assuming that Bob and Alice, they share these pulses, they do what they call it comparing the bases, and finally they got a shifted key. With the shifted key is here 1 1 0 0, maybe 1 0 0 1 1 1 0 0 1 1 1 1 1 0, and etc. So they have essentially, depending on the protocol, depending on the key analysis and etc. And we assume usually this length of the key is unbounded, is essentially infinite. So they have really a huge, let's say, numbers, which if we believe in statistic, usually this is 50% of what they essentially they shared, the signals that they shared, because 50% of the time Bob will be in the wrong base. And then after the, let's say, shifting, what they do, they check the amount of error. So from these signals, Bob picks up several of them, let's say in these cases, 4 of them, and ask Alice that, hey Alice, for the first signal I got 0. Alice says, yes, I sent 0 to you. And Bob says that for the 10 signals, I got 1. And Alice says, no, this is wrong. And they pick up this one as an error in the key that they have it. So they share, let's say, about 10% of these, let's say, information to get what are the amount of errors there. So they get the amount of errors to be eta. And this error is extremely important to analyze the quantum key distribution. We call it usually Q-bar, quantum bit error rate. And depending on the protocol that you do have, the error cannot hit a threshold. The threshold will be dictated by the protocol that you are using. And in some cases, when you have error reaching to a certain threshold, then you cannot trust to the channel. So we have performed a very complicated setup, which we did not restrict ourselves to by dimension, but we use the power of orbital momentum having access to higher dimensions. And we perform a survey on the QKD protocols, many different type of protocols. And we compare them all together. So for like, for example, BB84 protocol, Eckert, and many others, SIG-PO, VM, round robin, etc. And we check all of them together and see what is going on. For example, if you go with the dimension 7, these are the mutually unbiased spaces. This is look like the P space, and these look like the X space. And even you can check them. If you project each one on the other one, you will get 1 divided by 7. So they essentially they are conjugate quantities. And if Alice picks up one of those, which is let's say -3, then with 100% you can project them if you are in the right base. If you select the other one, which is -2, then again you can project them with 100%. So if you are in the right basis, you can get the proper projections. However, if you choose the wrong base, then the projection of these states on the others one, they will be unbiased. So you will get a probability of 1 divided by 7, and the same scenario for the other case. So they are look like XMP, as I say, that there is a threshold in or a limit in the measurement. So this is the QKD protocol. I'm getting the projective measurement of projection density matrix, which essentially you will get when you are in the right base, you can define the state perfectly, like this one and this one, because here you are sending in X and you are projecting in X. Here you are sending in P and you are projecting in P. Then you will get 100% the information. However, when you are in the wrong base, you have absolutely no idea. So we use this technique to do the encryption in a higher dimension. Instead of sending 1 bit of information, we were able to send 1.7 bits of information. And in the experimental result, also we had about 16% of error. And also, we implemented the cloning attack to the system. I just described that we have cloning issue. However, someone can build up an optimal cloning machine, which means that taking a pure state, on the other side, they can get 2 clone system or 2 clone states, but they are not anymore pure. They have a reduced they reduce the purity, and you have partially mixed states. And Alice Eve can pick up one of the base photons and send the other photon to Bob, and looking for the measurement to be done, and having access to quantum memory, and later on doing the process on the information. And so we performed the Hongu-Mandel or Fern-Lauden experiment. I don't want to go through this. It's a long discussion. Maybe in another talk we will discuss about that. What finally we got that due to the cloning attack, which is this machine essentially in the laboratory, we reduced the uncertainty. We reduced the certainty in the measurement when they are in the right basis. So previously, those diagonal states, they were 100% detected in a proper way, but now there is a limit there, which is the cloning attack limit. And as a consequence, you will see that the key has a lot of problem. And if you compare the two scenario, when you have a secure link and when you have a link which is unsecure and bothered by cloning attack, then you will see that the amount of error that you are introducing is not anymore 16%, which this 16% is due to the experimental imperfection. Now, due to the cloning attack, now the error is increased to 57%, which is hugely high, and it's really high. And that tells us also that if we use the benefit of going to higher dimensions, I don't want to talk about this, but maybe next time. If you go to higher dimension, you will see that the presence of Eve will be more clear in the higher dimension than lower dimensions. So going to higher dimension will give us the possibility to having a message more secure and also sending information much higher than the dimension 2. So I will stop here